Yeah, so good morning, everyone, and it's really a pleasure being here because I remember being here when we had the first AstroInformatics conference back then, and I thought, oh, cool, someone invented a field of research I'm perfectly matching in. So I'm very happy to be here now, 9 years after we had the first AstroInformatics conference. And because we always strive for connecting disciplines and get exchange from other fields, it's also about, how can you transfer knowledge from one domain to another? And I'm just talking a little bit about some projects we did together with weather forecast people. So my talk is about photometric redshifts and how they improved weather forecast. And it's, of course, if you think of the Event Horizon telescope, it's, of course, about black holes. And we all know black holes are somehow involved in our climate and weather here on the Earth. But what the connection really is methodology. And I will try to use the next remaining 24 minutes to explain what it's actually about. So we often have to deal with regression problems in astronomy. And one example for regression problems here actually is how do we derive redshifts photometrically? And how do we estimate redshifts photometrically? And therefore, we have to solve those regression problems. And it's really that simple thing. So you just say, I have something I call my model. My model gets a certain input vector or feature vector x from n-dimensional space. And I want to predict a certain value y. I want to have a simple estimate. It's that simple. This is a regression problem we want to solve. And actually figuring out what features go in, what model to be used to produce proper estimate, that's the challenge of finding a good predictive model. So what is estimating photometric redshifts about? It's, in principle, we are interested how a certain observed wavelength is shifted with respect to its rest frame wavelength in laboratory, where we would measure it. And here I just sketched an example of the Sloan Digital Sky Survey. You see spectra taken with Sloan, one of a quasar at a redshift of 3.81 and one of a quasar at a redshift of 5.31. And in principle, you see in the background the photometric filter bands. So if you take pictures, not do spectroscopy, you of course integrate the spectral energy distribution within those filter bands. And now the question is, if you just take a picture, it's of course quicker than taking the full spectrum. Based on the images, can you tell me which one is the one at 3.8 and which one is the one at 5.3? And that's actually the challenge here when you want to estimate redshifts photometrically. You just have the filter bands and you want to integrate it out. Very rough introduction for those from computer science. So if you do so, and that's something I presented on a poster back then when I was here at the first AstroInformatics conference, so it's quite old stuff. It's, in principle, you get plots where and this experiment was done with all quasars back in the Sloan Digital Sky Survey in the data release 7, quite old stuff. And if you now plot the spectroscopic redshift, you consider ground truth, so the redshift measured with a spectrograph, and you plot, on the other hand, the estimated redshift, and here a simple k-nearest neighbor model was used. The ideal solution would be the middle line, but you can see there are certain errors. And that's what it is about. But what you can see here is already how things are changing. In the past, we were doing point estimate. So we had a model that was estimating y as a discrete value. But we have a lot of uncertainties in our models. And those uncertainties are tremendously important to improve our science, because we want to say, how much can you trust the result? How correct is the result? And we want to be as honest as possible. And within this talk, I want to motivate a better way to actually do that. So we have uncertainties in the inputs. We spoke about it a little bit yesterday. We have our measurements errors. And that's what physics in general is strong about. A measurement is always a value and its error. In best case, a likelihood function, actually. And we have model uncertainties. Perhaps we are not capturing all the degeneracies we have when trying to solve the regression problem. There are a lot of things that might not be expressed correctly, or where we are just lacking data when training a model. And therefore, we need to have uncertain estimates. And in principle, it's going from predicting a single value to properly predicting a probability density function. That's what it is about. So you can estimate likelihoods and check it. So, and if you have now such a probability density function, the integral sums to 1, then you can just say, okay, given the two values a and b, what is the actual probability of my value being in that interval? And you can solve those things really easily, and you get out probabilities. You can check what is a probability density at a certain point. You really can do science with this. And that's tremendously important, because if we now go back to the question of photometric redshift estimation, we will see, yeah, single modal estimations are not the correct thing. What I plotted here is for a given object with a true redshift, the red line, around 2, I plotted the nearest neighbors. In this case, I think it's the 64 nearest neighbors. And what you see is the neighbors are selected based on vicinity in the input feature space, based on the photometric measurements. But you see clearly there's a big spot, and down here I plotted a histogram over those. So we have at least a bimodal case with one peak here around 1.7 and another one around 0.7. And the reason for that is it's a degeneracy in how the filter bands look like and how we want to regenerate or reconstruct the spectral energy distribution of a hidden spectral model, and therefore we can't say clearly. And if you now fit a Gaussian mixture model with 5 components, you see you have different components. And it's clear from that case that answering with one single value is probably not the best thing to do. Given the stated problem we have to solve, we need to have a proper tool to express it. And the problem we sometimes have is we often come up with reinventing the wheel in astronomy. We had done great inventions, and we had done some inventions that are not so good. Of course, the root mean square error is a proper measure. Don't get me wrong. It's probably measuring some things, but it's not measuring how a distribution looks like. And the question is, if you have a distribution that is bimodal in that case, just using the mean is probably the place with the lowest likelihood or probability density you shouldn't use for your evaluation. It's like a Tesla sports car, automatically driving, approaching a traffic light that switches to red. So you have just the option slow down and brake, or accelerate and keep on going and make it. If you just keep on going with a intermediate speed, you will crash. So the root mean square error is not capturing the shape of the probability density distribution, and therefore at that point we have to be a little bit careful. So it's really questionable whether we are using always the correct measures to evaluate performances of models. The next thing is we develop tools like stacking PDFs. It's, for example, also written in the Euclid mission statement. And here you have 2 different models, and I predicted very precisely, very narrow distribution. One is above, one is below. The actual, for this case and for this case, likelihood is close to 0, or probability density is close to 0. I would say it's a horrible guess, because we pretend to be very accurate, even though we are not. But by stacking them and checking how much integral of the area of the stacked PDFs is outside a certain area, it's not a proper measure for outlierness. Because sometimes it's better to have broader measurements that are within the reported uncertainty, and use those, even though they would have something that would be considered outlierness in those stacked PDFs, or in the case of bimodalness, it's better to be on top of one of the peaks than this. So we really have to ask ourselves whether we are using the correct tools. And that's now where the connection starts with weather forecasting. So back then, Antonio and I were struggling with a problem where we wanted to optimize properly, and we figured out the tools commonly used in astronomy for evaluating performances are not the best actually for what we want to measure. And in weather forecasting, they always have to deal with, I want to predict temperature for tomorrow, and I want to predict an uncertainty on top of it. So saying tomorrow is 25 degrees Celsius plus minus 0.0001 degree is definitely telling I'm lying, because no one knows with that precision what the temperature will be. So it's better to say tomorrow is 30 degrees plus minus 20 degrees, because my uncertainty is quite large, but at least given my capability of predicting the temperature, it's honest. And those tools, those proper evaluation tools like the CRPS, are considered something like a truth serum for those things, because they are measuring sharpness and calibration. And the CRPS in this example, it's explained, you just take the PDF, transfer it in its cumulative distributive function, then you take the Heaviside step function, that is a CDF of this true redshift, and then you just look at the difference, the area, and integrate over the squared area there, and that's telling you a lot. And if you think about it a little deeper, you will see having broader ones that are still precise within your estimates, it gives you good values. If you're off and very steep and sharp, it gives you really bad values. So it's measuring the distribution, the shape of the distribution, alongside with the actual prediction. And you only get a good result in the meanings of CRPS if the predicted distribution is the same like the underlying distribution creating your errors. And that's essential in that case to measure it correctly. And with the CRPS, you can now measure those things better. And you get a grip what the uncertainty distribution looks like. There are other evaluation tools like the probability integral transform, where you just evaluate the CDF at the true redshift. If you're always in the middle and have a broad one, you get a 0.5. And based on that, of course, if you now plot a histogram over the PITs, you get an underdisbursement if you are too narrow. Think of it, your predictions are really 0.0001 degrees in uncertainty. You will very likely hit a 0 or 1 because you are very likely above the true value or below the true value with your prediction. You are over-dispersed, like I was in my case saying plus minus 20 degrees. Yeah, I will always hit it somewhere in the middle, but it's not uniformly. If I have a bias in my prediction, it will be slanted because certain values are preferred to other ones. And only if it's really well calibrated, I get a uniform distribution. And a simple visual tool is really telling me a lot about those things. So this is what we learned from weather forecasting. Statisticians there really took care about weather stations not predicting with certain high accuracy things where they couldn't do so. So they came up with the CRPS. And Tilman Knighting is luckily working at HITS, and I had several coffees with each other, so we learned about the problem from weather forecasting. So if you now take a nearest neighbor approach again, go back to the example I showed you before, but now say each point estimate is, instead of being a point estimate, a single Gaussian with a sigma of 0.01. So over precise, you see we are severely underdispersed. So we are just lying with our uncertainty, and the CRPS is quite bad. And note that along this axis, you now get a sum probability density. It's not a value, it's a probability density function you have along one axis. So if you now take a single Gaussian and make it wider, you see, oh, I have some outliers at the upper and lower end, and in the middle, it's over-dispersed, it's too wide. So what if I now take my nearest neighbors and calculate the mean over the nearest neighbors and the standard deviation and use this as basis for my prediction? I already improve my results a lot. So I just look, what do the nearest neighbors look like, and use it as a basis. But it's improving, but it's not perfect. Why? Because it's a single Gaussian. And remember, I was talking about multi-modalities being the tricky thing. And therefore, if you now take a mixture model with 5 Gaussians, use the nearest neighbors, fit a mixture model to the nearest neighbors, you get the symmetries out. The symmetries because you have multi-modalities telling you you have a degenerated problem. And if you use a random forest, it's a quantile regression forest. If you use it in combination with the mixture model, is even improving. And then we used something very simple called mixture density network. And with the mixture density network, it was nicely calibrated because we used as a loss function at that point the CRPS for training, not the likelihood. We have a network, and I will show it on that slide here. We have a network, and that's the mixture density part, where we have a fully connected part with the inputs, and we predict as outputs the component of my mixture model. And the mixture model gives me now my probability density distribution. And those ones I can estimate with the CRPS and use this as a loss function. Sounds trivial, but Antonio and I had been the first doing so. Now people like Andrew Ng figured out it's really clever to do it if you have to deal with uncertainties. And it's better than using the likelihood because you take calibration and sharpness into account and not just sharpness. So it's subtle details. Back then, we were dealing with images and thought, oh, yeah, always this feature selection. That's so annoying. Some just put images in. So we took a very simple architecture. And it's not about sizes of architectures. It's about concepts and methodology. We took a very simple architecture, 2 or 3 convolutional layers, taking the images, producing a huge set of features, using the features for a fully connected part, predicting probability density distribution. And on that data set, we achieved by far the best results ever achieved on that data set because we could exploit all the information content and stored in those images. And that helps a lot. Through IVOAA, we had a chance to easily access the data. This is often a problem. Listen to Antonio's talk. He will talk a little bit about that. And with those things now, we trained it. And if you just take a plain random forest and use as input all the individual pixels, you get a nicely calibrated one. It's a flaming sword of truth. That's what we call it, and it was on Antonio's PhD hat. But of course, if you use a mixture density network and then a deep convolutional mixture density network, you see that you really have the ability to improve your results. And you're improving over time. And you have the advantage of using more complex input catalogs, because the world is more complex than just being composed out of quasars. If you take quasars, galaxies, and stars as input sources and train your network with such a data set and just assign stars to have a redshift of 0, it intrinsically learns what is a cold star and what is a high redshifted quasar, therefore generates a nice calibrated probability density function, and you can evaluate the probabilities of belonging to something. And of course, you can figure out how old I am. So if you put my image in, you see I'm around 9.9 giga-years old, and if you take a rotten fish, it's 3.5 giga-years old. I'm using always this example. We have to be careful when using deep learning. It's trained on one data set, but it will produce results on every data you put in. So now the question is, how do we go to weather forecasting? So weather forecast simulations, in this example, I'm using some from the European Center for Medium Range Weather Forecast, ECMWF. And here it's just exemplarily shown how it looks like. It's a temperature map with a pressure map, and I have wind in 2 components, and I have clouds, and I have many other parameters, actually. I have the air temperatures 2 meters above ground. I have wind speeds at different pressure levels. I know what is a height at which I reach 500 hectopascal. A lot of things they produce in their simulations. So they have a different problem than we have. They get a lot of simulations, and the question is, how can we predict a single value, a single temperature for a single station? Because what they have, and this example, of course, is Germany-centric somehow. In this example, we have 537 weather stations with measurements. And now we want to check how good are our measurements with a lead time of 48 hours, so 2 days in advance, and compare it with actual measurements achieved on that day. And for the stations, we have longitude, latitude, something like orography, land and sea level stuff. And we have data of, from 2007 until 2015, 9 years of data. and in principle the parameters. And what they usually do is they use the things for statistical post-processing. They want to know how do we have to interpolate those 81 by 81 maps I've shown you here. How do we have to interpolate them to actually know what is the weather at a certain station? So they take the ensemble of 50 simulation runs they do and just represent every value at every grid point with its mean and standard deviation. So they compress the whole ensemble. And back then, the state-of-the-art method allowed them to post-process the simulation runs for the forecasting to a CRPS value of 0.81. So just taking the input data from the simulation, creating means, and post-processing it with a simple model, they could improve it towards using the raw data to a value of 0.81. And then they heard a talk by Antonio in our scientific seminar series. We spoke about those things, and they figured out, in principle, what you are generating is exactly what we want, and the input data here we have as well. So let's forget about the deep convolutional part. Just take a mixture density network, and actually for simplicity, we just have one Gaussian. So they took our code, stripped it down by a lot, and just took a simple mixture density network they haven't been aware of. They haven't been aware of that you can train those networks with your own loss function. It's not always a likelihood. It can be a CRPS, whatever you want to be. And now created a fully connected network where they put the mean and standard deviation of the temperature at 2 meters height, plus an embedding to have station-specific corrections and compensation terms being learned, because all the others trained individual models for each of the stations, and they trained a global one just with a little correction term. And they had the auxiliary variables. And with a single hidden layer, they reached a CRPS of 0.78, published it last year, and it seems that it's now the state-of-the-art, becoming the state-of-the-art method in weather forecasting, a method that actually was introduced to measure redshifts of quasars photometrically. Then we spoke a little bit and figured out they are using not our architecture, they are using a tiny bit of it. So we thought, okay, what happens if we take longitude, latitude, altitude, and orography of each station, simple fully connected network to 8 nodes and then down to 2 nodes. We get something like an embedding we can plot. So for each station, we get an x and y coordinate out and use the x and y coordinate as correction terms for each station individually. And then we can plot a map of Germany with the individual correction terms. And if we do so on a video, and you see while it's training, it's learning coastal distance is important, as well as altitude, and also the River Rhine seems to play a certain role in how you correct it. The advantage now is you have a model where you can take the coordinates of your mobile phone and use it and project it through the model in order to get it. And you get interpretability out by introducing an artificial bottleneck of dimensionality 2. You can understand things. And bottlenecks are, of course, the next big thing. We tried the DCMDN on the whole ensemble. 50 ensemble simulations, 81 times 81 node grid points times 17 physical parameters for 535 stations over 3,667 days was a little, it was a little bit too much of data. So we thought, let's use autoencoders, and we auto-encoded everything. So we first took the full ensemble and thought, project it down. Here you see data from the 14th of February. Here, a summer day in 2010. We project it down. All the red points belong to the 50 ensemble members of this example. All the blue ones belong to this one. And here you see the individual reconstruction. And what you see, auto-encoding such a complex data set to 2 dimensions, no chance of doing it. So we started auto-encoding temperature only. And yeah, it sort of works. It figured out there are hot days and there are cold days. Great. At least it learns a little bit about temperature distribution about Europe and about somehow different weather regimes. But if you think about it a little bit closer, then you figure out in principle, you are interested not whether it's a cold day or it's a hot day. You are in structural components interested. And that's why we took a temperature deviation from the mean of each layer of the other ones. And we auto-encoded it. And we took the next one, that's clouds, and we auto-encoded clouds. And a lot of cool projections came out. And you see, it can spot differences. And it gives you the ability to interpret it, but you have to be in metrology. And then we auto-encoded something like pressure, but I figured out, oh, they predict pressures for the surface, and that's not correct. So we corrected the pressure by the mean pressure over all days to get rid of the Alps that are a little bit higher, and therefore, and it collapses because somehow the data is really too complex, and the auto-encoding at that point fails. So in principle, with all the projections, temperature's okay, clouds are sort of okay, pressure, forget about it. It's so complicated that 2D won't work. Wind, don't ask me. Geopotential, also a complete failure, so sad. So, but in the end, what we did is now, we created some additional inputs to the previous architecture. We take something to correct for location. We have something to correct for weather regime. And if we just use those simple extra inputs, we compress the data first, we add interpretability, we are able to do a CRPS of 0.76. We reported it back. They're happy. We are having a lot of discussion on that. And in principle, yeah, compressing complex data really might sometimes add interpretability. And if you do it properly, you can visualize it. And we have seen a great talk on visualization yesterday. And that's a point that's, I think, connecting a lot of disciplines. And really use a proper score for training. It really helps a lot. And don't use the mean square error or just the likelihood for a problem that demands a better representation. We are now working on seriously better. This was simple examples we showed to them. It's their work. They should do it. But we need better dimensionality reduction techniques to get better results, I guess. Time series analysis was completely left out. And with the things we learned, we want to now revisit photometric redshift. Thanks.